Point. Yeah. Slideshow from begin. Okay. There we go. All right. Wow. 11, 12. We're down quite a few people today. Huh. Okay. Welcome back from spring break. We're getting to the end of the semester. I know, as I can tell, a lot of people left after spring break and decided not to come back, I guess. No, I mean, to be fair, I know a couple of people are joining us remotely for various reasons. But yeah, I don't know. It is, I was thinking about that. It's getting to be that time of the semester where people are just like, ah. Oh, you think more people would show up if I gave more extra credit options for the homework? Okay, well, so that's weird because I was looking at the grades and they didn't look that low. There are like 2 assignments where they were low. Oh yeah, I never said that, did I? Yeah. Okay, fair enough, fair enough. But I mean, I did look at the grades and they didn't look, there were 2 assignments that were low. You're right, I can find some extra credit somewhere probably, but there were 2 assignments that were low. The rest of them, I thought the grades actually, like the last assignment, the grades were mostly like almost all A's. The assignment before that, they were almost all A's. I think it's pretty typical in the beginning for people's grades to be a little bit lower as you're. Yeah. And plus, I think you're getting in the groove as the semester goes on. So, I mean, I hear you. I hear what you're saying. But I don't think that it's the lack of extra credit that has caused people to not show up. I mean, I think your point is fair, but I think those 2 issues should be disentangled. Yeah, we should talk about the final. It's not going to be anything like the homeworks. So, all right. Yes. Solutions for the what for what? Oh, you don't know what the right answers are? It's still confusing. Okay, well, maybe we should go back and revisit some of those questions then, actually. If there are things that you still don't understand about earlier assignments, we should go back and revisit those. I didn't realize that that was the case because usually you get, you know, information on your assignments about what was wrong, right? Okay. Well, I'm not going to post the answer keys for the assignments because I cannot recreate assignments every year. I just, I cannot. I cannot tell you how long it takes to create these assignments and the answer keys and the data sets and get everything to work. And literally, if I had to do this every year, I wouldn't teach. I would probably stop teaching the class, to be quite honest. I'd hand it off to somebody else because, like, yeah, I'd be like, oh my God. I mean, it already takes a million years to get ready for this class. Yeah, I mean, I'm glad to talk about any questions that people had troubles with during class. I'm glad to meet with anybody during office hours if you're confused about a question from homework. Like, kind of makes me sad that there might be questions from homework 2 that you're still feeling unclear about. And it's like, I don't know what, March 23rd. So that's, I mean, like if there are things that you're not clear about, bring them into class and we'll talk about them. Anything from the old homeworks. If you think, I mean, again, if it's something that's common to everybody, we should talk about it in class. If you think it's something that like, you think you might be the only one and everybody else has moved on, then come to office hours. I mean, and we'll get those things cleared up for sure. But I'm not, I cannot do that. All right. So, other questions about, and I'll find a place for some extra credit, but I was looking at grades over the break and I don't think they look bad. I mean, like in general, most people seem to have A's right now. So that's, or A's or high B's. How about that? At least that was the way it looked to me as I was eyeballing it. So I wasn't too worried, but like, you shouldn't expect to get 100 on every homework assignment either. Like, it's not that kind of class. Like, I mean, I can tell you when if I were taking this class, and not now as an instructor, I think I get hundreds, but if I were taking this class as a student, I mean, I wouldn't have gotten hundreds. I didn't, when I took this class, get hundreds on, I mean, again, they weren't the same assignments, but sort of a similar ilk. You should expect that there are going to be these little things that you haven't totally mapped. I mean, this is like like modeling is like this incredibly deep pool, right? And you're kind of wading into it. And it's tough because there's just a lot. I mean, I'm still learning things every day, every week, every year in this area, and I've been doing this for over 20 years now. So it's a lot. It's a lot. I mean, I recognize that. And I mean, I don't know if it's good or bad. I guess it's bad. Like, you were going to have learned a ton at the end of the semester, and you still have just scratched the surface of this deep, deep pool. So anyway, but if there are questions, like if you have questions about things you don't understand, come to me. If you have questions about your grades, come to me. Let me know. I'm glad to talk about those things. And again, if you think there are things that we should talk about in class that we need to revisit, if there are concepts that are key that you're still not understanding, then we should talk about those. And there will be time for a review session. We will take a chunk of the class on the last day. I mean, usually it's the whole class, but we're running behind, so we'll see. It'll be at least half of the class on the last day will be like review for the final. And I think the best way to run that review, the way I usually do it, is people come in with questions and we just like talk about them, right? Like people say I'm still a little unclear on what the difference between this and this is, or I still can you explain that thing again? And I'll just go through whatever you want again. So on that note, let's talk about what the final is. Yeah, well, don't be too stressed. So here's the deal with the final. Well, first of all, so I want to apologize. There is a typo on the syllabus that is sort of a holdover from fall of 2020, which I will honor if I need to, but I would sort of prefer not to. So in fall of 2020, you'll remember that everybody had to go home after Thanksgiving. And so it said that the final would be remote. I would really prefer to have you all here to do the final. Again, if somebody has an issue, you're not going to be here because you thought the final was remote and you need to do it remotely, then you can do it remotely with the, with the security camera system thing that they do for remote finals. But so like if you need that, that's fine. And there are people sometimes who have, who work with the Center for Students with Disabilities and take the final over there, and that's totally, that's fine, like they run that, that happens, just generally every year, and that's not an issue. But I think it's better if you can swing it to come here for the final, because I'll be here, and if you have any questions or if anything goes wrong or whatever, it's just easier to like be here to take it. So what does the final look like? Well, It looks really different from the homeworks. And that's purposeful. So it is, there's no running of M plus. There's no output. There's no there's no interpretation really. I mean, it's really foundational. So it is multiple choice and short answer, and it's really an assessment of the foundational concepts in the class. So why is it so different? Well, again, that's purposeful. I feel like, the homeworks are one thing. You learn a lot from the homeworks, and you learn how to run M plus, and you learn how to interpret output. But, it's like every week you're doing this discrete thing. Hey, that's weird. Every week you're doing this discrete thing, right? And I think a person could sort of go along and get very compartmentalized from week to week to week and sort of do the homework and maybe lose sight of the big picture of like, what the heck are we doing here? How does all of this fit together? You might be feeling that way yourselves at times, right? Like, okay, let me just get through this week. So the final is really about pulling everything together and coming back to the basics and the foundations and thinking about what is it we're doing? Why are we doing it? How does everything fit together? It is open book and open notes. You can bring other books if you want. You can bring any materials you want. That's right. You can't obviously use other people, right? But other than that, you can, you're free to use whatever materials you want for the final. So it's not a test of memory at all, but it is I think a good test of understanding, of whether you really understand the stuff. It shouldn't, because the answer, like I said, it's a combination of multiple choice and short answers. There aren't any like lengthy essays. Short answers are things like, like taking a path diagram and figuring out what the indirect effects are, or might be write a sentence about something, but it's not, there's no lengthy writing involved. Yeah. Yeah, you can have, that's fine. You can have PDFs and stuff, all the physical materials. Yeah, I don't think that your home, there might be little things here and there from the homeworks that might, but it's not really like the homeworks. So, I'm not saying like, if you have your homeworks, it wouldn't hurt to bring them with you, but I don't think the homeworks are really where you're going to be looking. Like, I don't want to say don't bring your homeworks, and then you're like, this is my homework, and you told me not to bring it. But I don't think that's really where I think the PowerPoints, really, I feel like just about everything that you need to know is on those PowerPoints. Yeah. Yeah. If you want to bring an iPad, or if you want to bring a laptop and have that open, again, with the, I don't want you communicating with other people, right? But you can. Yeah, so this is the question. So would you rather have the exam electronically or on paper? I could go either way. Electronic? Okay. On paper. Yeah. I'm trying to remember how that worked. It's not a lot of writing. It's very, very little writing. I'm just trying to remember. I think it's easier on paper to scribble stuff down, but we can. No, I do. I do know what you mean. I do think it's probably easier on actually. No, like I said, there's not more than a sentence per question of writing. It's most of the writing is like, it might be a little mathy or a little pathy, but it's not so, there's not mathy or pathy, but it's not really, there are no like essay questions or anything like that. So I do think it's a little bit easier on paper. Like if you're having to trace through a diagram and figure out, I think that's easier to have on paper personally, right? So, okay, so let's go paper. Yes. Yeah, so I'll give you all 3.5 hours for the exam from like 9 to 12:30. Anybody who wants like 3.5 hours is fine. I think there becomes a point at, I think the exam should take about, most people about 2 hours. I don't know. What do you think, Jocelyn? About 2 hours? Oh, okay. What? Yeah, you were one of the, yeah. So we'll go with the 3.5 hour time slot. I think that should be sufficient. I worry about going too long because with all your materials and stuff, I mean, so my husband teaches here too, and he teaches a class and he gives unlimited time for exams because he doesn't want people to be stressed out, which I think, that sounds really nice. But so 1 year, he still does this too. I'm like, I can't believe you still do this. So 1 year, and it's open book and open notes. 1 year, he was at the office until almost midnight because somebody stayed for 10 hours, like perseverating on one question because they weren't sure about this one question and they just couldn't let it go. So I am saving you from yourselves by not giving you more than 3.5 hours because like really it shouldn't take you that long. And like at a certain point, you just need to like release yourself from the exam and go on with your life. Cause like, again, they're short. I mean, it's like, I think it's 25 questions that are multiple choice and short answer. If you can't get 25 questions done in 3.5 hours, like you don't know the answer to that question. Like you're flipping through, right? Like you're going from book to book to book to try to find that answer. And at a certain point, we all just need to move on with our lives. It's one question. No, they're not questions like the assignment questions. They're not. They're much more like what you would expect to see. They look much more like prototypical exam questions. Yeah, well, then that's a good thing. Like, there's no opportunity for you to write a lot on this exam. Like, the questions are all, there aren't any essays. It's all like I said, I mean, I would say it's 2/3 multiple choice probably, and 1/3 incredibly short answer. So, okay. And again, and it's open book and it's open notes, and you have 3.5 hours for those 25 questions, which do not involve any essays. I'm not saying it doesn't involve some like thought, right? I mean, of course, right? You're going to go through and just be sure that you know what you're, okay, what do I want to make sure I pick the right answer? Yeah, of course, you're going to think about stuff, but it's not like, what? There's no M+ code. There's no output. There's nothing like that. So it's very different from, and deliberately incredibly different from the homework assignments. Not a lot. I mean, there's a little bit of very simple computation. Wouldn't hurt to have a calculator just in case, but there's no like hardcore difficult computation, right? But obviously there could be simple things that you're asked to kind of figure out. Oh yeah. To be fair, that I gotta say that one question it's funny. I changed that question. I totally changed the path diagram for this year. There was this, and I didn't realize it didn't look like that complicated until I went to like do the, I was like, that's a good diagram, right? And then I went to do it out, and I was like, oh, this is a pain, man. Yeah. Okay, we can go back and re-examine. Go back and re-examine that question on homework too. So that that was a pain in the butt question. I will agree. There's nothing that's that onerous on this. Yeah, that was a bad. That was a bad. You know, it was funny too because I had this other example, and it was about fathers and sons and their education levels, like from 1960 or something. And I was like, God, it's 2022. I can't give this. This is so, gross. And then after I changed it, I was like, yeah, I want to go back to the fathers and sons. This was like a lot easier model. What was I thinking? It does. There is that, and it's good to be able to do that, right? But you only want to have to do that. Yeah, you only want to have to do that you only want to have to do that just to make sure you understand how things are going. I mean, there are times when you really there are times when I sit down and I have to do that kind of stuff. So it is, it is useful from that perspective. I mean, we haven't talked a lot about covariance algebra in here, but like knowing the tracing rules, knowing covariance algebra, like if you're going to go deep into this stuff, it's super useful. But yeah, that was it's not a horrible exam, but it is, it is a test of your understanding. And I will say this, people have said, like, I'm not tooting my own horn here or anything, but people have said I'm pretty good at writing questions that aren't tricky, that you can get right if you know it, but where if you don't know it, it's hard to guess. So, which, as a measurement person, I kind of pride myself on that, right? I've been trained on how to write good distractors. So, but yeah, but it'll be fine. It'll be good. Live through it. You get a t-shirt. I survived SEM. Yeah. There you go. I should give out t-shirts, shouldn't I? What about Slack? Doesn't Slack give out free t-shirts? Weren't they going to do t-shirts or something? Yeah, I know. You don't get free stuff anymore, right? All right. Well, I'll have to think about that. All right. So on that note, any other questions about the exam? So the plan is exam week. We'll do it in here. You'll have 3.5 hours. And we'll spend a big chunk of the last day of class reviewing. So, and I guess I should say this too. In terms of how should you best prepare for the exam, I would say, well, you don't have to memorize anything because it's open book and open notes, right? So it's not like you have to sit down and memorize stuff. But I think the best way you can prepare is organize your stuff, and in the process of sort of organizing your stuff, that will help you to kind of go back and sort of revisit those topics and maybe see how everything fits together. And that's really the best way to prepare, is just to kind of go back through your stuff, get it organized, and sort of think about, how does this fit together? Where did we come from and where did we end up? And you'll all be fine. I promise. Yeah. Yeah. I would prefer not anything on the internet. I think that also becomes a rabbit hole. Again, if you're unlikely to be able to, if you really have no clue, Google the answer, and that's probably not a good strategy. Yeah. Yeah, Kenny's book is fine. The PDF of Kenny's book. I mean, his book. How if I just bring Dave here and he can be your phone a friend? Yeah. That's right. I mean, again, I think you gotta understand, this isn't I know some people write multiple choice questions that are who was the dog that died of blah, blah, blah. It's not nitpicky facts that you might have missed in your readings or in my lectures. It's not like that. So I don't think that going out on the internet is actually going to help you. It's, do you actually understand the fundamentals of what we've been doing? And truly I really believe everything you need to get an A+ on the exam is sitting in the PowerPoints that I have given you every week. Like, I'm not going out and finding stuff that we haven't talked about in class. It's all stuff we've been talking about all semester. Things like, I mean, you can imagine what some of the main some of the major hits are things like chi-square difference test, right? And understanding, understanding how to count numbers of parameters and degrees of freedom, knowns and unknowns, and I mean, all that kind of good stuff. So I don't think, if you can't find it in your PowerPoints, you're unlikely to find it in some, sort of esoteric source. Yeah. No, I'm not going to be, no, there's not going to be stuff on like when I mention, oh yeah, recent research is blah, blah, blah. You're not going to ask you to do something with dynamic fit indices of McNeish, or when we talk about the STARTS model for one slide today, there's nothing on the STARTS model on the exam. I mean, it's not the little nitpicky stuff. It's the big stuff. I want to make sure you've got the foundations, the big stuff down. The tracing rule. I mean, that kind of stuff. Yes. What are direct, indirect, and total effects? How is a total effect different from a model implied correlation? You better know that. That's guaranteed to be on the exam. But like, those I feel like are fundamental concepts that by the end of the semester, I want you to be solid on. It's that kind of stuff. So bring in anything you want, but you're not going to find the answers like lying in some strange dark corner of the web. I hope, unless somebody memorized all the questions. No, I change. No, the exam I change. All right. Other questions about the exam? Feel better? Kinda? All right. Yeah. Uh-huh. Oh yeah. That's a good question. I mean, we've talked about some ways, but it can be tricky actually. And one of the topics that we skipped that maybe we will come back to if there's time, I would like to come back to if there's time, is actually there is a technique that you can use to determine whether models are nested or equivalent. It's like an M plus. Well, it's not M plus per se. It could be done in any SEM program, but it actually involves using an SEM program and sort of setting up a couple of models and fitting them. And that is like the surefire way to tell if models are nested, equivalent, or neither when it's a really difficult model to tell. So like for certain models, it's really easy to tell. I mean, there are certain general rules and it's just easy and you'll get that and you'll know that. But it can be, there are situations where it can be really difficult to tell if two models are nested or equivalent or neither. I mean, these models get pretty complex. So I can't say like off the top of my head, here are 3 simple rules and that will always tell you, whether these models are nested or equivalent or not. There's a whole slew actually of rules for equivalent models, again, that we didn't really talk about. But that gets complicated. So the easiest thing is actually a little jiffy trick that I would like to show you, but we'll see. Other questions? All right, let's talk about autoregressive models. Here we go. Okay, so just to remind ourselves, for the last 2 weeks, we were talking about growth models. So this is our 3rd week of talking about longitudinal models. And really, again, we could easily spend a semester talking about longitudinal models. I would love that, actually. I love longitudinal models. They're super fun. But this is it. This is our last week of longitudinal models. And then next week and the week after, we're going to do multiple group models. We're going to do measurement and variance next week. And then we're going to do multiple group SEM the following week. I think that's right. I'm sure that's right. Okay. So So you'll remember we talked about growth curve models the last couple of weeks, and today we're going to talk about autoregressive models, which it's just a completely different way of thinking about the process that's underlying, you know, the data generation process. So the model that you sort of, the conceptual model that you have for sort of how these data have come to be is completely different for an autoregressive model than a growth curve model. They make really different assumptions about the structure of the variance covariance matrix. And, you know, again, you as a researcher, as an analyst, are going to have to determine for your own data, for your own sort of research studies, whether, you know, you think you have some sort of an autoregressive process or whether you have some sort of a growth process. I mean, theoretically, the data, you could have the same data set and fit it as an autoregressive model or as a growth model. Obviously, if you do that, one of those models is going to fit better than the other one. And so I guess that's one way to determine what kind of model you have. But again, you know, theoretically, I think you really want to be thinking about these, you know, they really imply very different processes at play. So we're going to talk about autoregressive models. We're going to keep it relatively simple. I have some slides at the end on bivariate, on sort of cross-lag panel models. I don't know that we'll get to those necessarily. It would be, you know, it would be nice if we do, but for sure we'll get through all of the univariate autoregressive models. And you know, once you understand that, then it's not so hard to go bivariate. Okay, so just another note is that today we are totally ignoring means again. We're not, oops, are we short on? Oh, okay. Oh, did they not staple or? That's annoying. So today we're ignoring means. And again, so we're generally going to assume that all of our latent variables and our measured variables are centered, but like with autoregressive models are generally not actually concerned with the mean structure. So it's pretty common to just sort of allow the mean structure to be completely basically just identified, right? So there's a just identified mean structure. So there's a just identified mean structure, then nothing about the means is actually going to come into play in terms of the chi-square and the degrees of freedom, right? And again, for most of the models that we talked about in the early part of the semester, we had just identified mean structure. We didn't think about it, but I mean, that's pretty common. So we're not thinking about means today. All right, so what do these autoregressive models look like? All right, here's the deal. We're going to think about, actually, okay, let me jump to this path model picture. Okay, with an autoregressive model, we're basically thinking that where you are today is like a function of where you were yesterday. Where you were yesterday is a function of where you were the day before. So, you know, you can sort of think of it as like, you know, I am, right? I can, and so again, look at this. This is just like a regression model. And well, actually, very lengthy chain of regression models, if you will. But it's also, if you look at this, you could think of this as a mediation model, right? Where we have complete mediation here. And so if you think about that, I'm saying like, so this is reading scores in 2006 is what read 6 is. So this is like reading scores. And actually, this is the data that we'll play around with later. So these are school means on reading. So it's like, what was the school's reading? I mean, like, what was the school's average reading on the CMT in 2006? And how well did that predict the school's average reading in 2007? And then how well did the school's average reading in 2007, you know, how well does that predict their reading in 2008, right? And so on and so forth. So basically you're saying, instead of saying like, oh, there's some, think about our growth models, like we really had this latent intercept and this latent growth slope, and we were really interested in means, and we were thinking about growth over time. Here, we're not thinking about means, we're really thinking about covariances or correlations, and we're really saying, you know, where I am at time t is completely predicted. Well, not completely predicted in the sense that the R is 1, but the thing that predicts where I am today is where I was yesterday. And the thing that predicts where I was yesterday is where I was the day before, right? And that's what we mean by these sort of autoregressive parameters. So I'm regressing time t on time t minus 1. And that's really what autoregressive means, or autoregression. And so if you think about this, then, if you look at this drawing, you can see that, like, where I am for the second time point, that read SX7, is just predicted by read SX6, and then there's a disturbance. So for that very first part, that's just like a simple linear regression, right? That's really, really simple. And we're going to get a path coefficient, and that standardized path coefficient is often called a stability, because it's telling about how stable this variable is from one time point to the next, right? And again, if you think about like a standardized path coefficient, it's going to generally be between, -1 and 1. Actually, it's generally going to be positive. I mean, if you're talking about the same trait over time, it would be unusual to have negative paths, right? So it's generally going to be, between 0 and 1 for a standardized path coefficient. And the stronger it is, the closer it is to 1, then the more the stability, right? So again, if you could imagine, if really the correlation between time points were 1, then I could completely predict where I am today based on where I was yesterday. But that's not going to happen. Why do you think we never get correlations of 1 between 2 adjacent time points? Yeah, so first, one is measurement error, right? There's some degree of measurement error in my measure. So like this should be kind of rankling you right there, because what? I think so. Yeah, I hit record, so fingers crossed, it should be recording. So what was I saying? Oh yeah, so this should kind of rankle you at this point in the semester, right? Because I've spent all this time talking about latent variables, and here this is observed variables, right? So there's measurement error inherent in each of those observed variables, and that obviously is going to bias my paths. So we're going to move on from this model pretty quickly to an autoregressive model where we fit latent variables. But this is a good place to start. Okay, so one thing is measurement error. There's measurement error in each of those variables at each time point. What else? Well, if it's growth, I wouldn't expect the same score. Of course, if it's growth, this is probably not the right model for me, but yes. But even if it's not growth, there could be things that happen between time 1 and time 2 that would sort of disrupt or disturb, let's say, that would disturb the process. So, for example, like, so some people may not, if you think about what a correlation is really about the stability of rank ordering, right? If everybody's in sort of the same rank order across time, then you're going to get a high correlation. And in fact, this is kind of an interesting thing that people don't always think about, but like, you could have scores at time 2 could be, let's say, 10 points higher than scores at time 1. And you could still have a correlation of 1 between the scores at time 1 and the scores at time 2. The way that you would get a correlation of 1 between scores at time 1 and scores at time 2 is if everybody increased by 10 points, right? So if everybody increases by the same amount, you've held that rank ordering is the same across time, right? And so then you're going to get a high correlation because you can predict where somebody is at time 2 based on where they are at time 1. which again, so we're not thinking about means here, but the means don't have to be staying constant just because we're not thinking about them, so they can do whatever they want. But what I'm saying is people's relative standing, like this path is telling me about the degree to which relative standing at time 2 is predicted by relative standing at time 1. Yeah? Okay. And let's think for a minute too about what happens. Let's say the correlation between time 1 and time 2 is let's say it's 0.9. Okay, so that's a pretty strong correlation, right? So that means I can pretty well predict where you're going to be at that second time point based on where you are at the first time point. And now let's just assume for a minute that, and when we talk about these models, by the way, you can hold those stabilities constant across time. So we can run models where we constrain those paths to be equal across time. And that ends up having some nice properties, but it isn't necessary for fitting the models. It's sort of like when we talked about CFA and we were like, it's really nice to have, have unidimensionality. It's really nice not to have correlated errors, but like I can do those things, right? But from a modeling perspective, I can sort of say some nice things if I can make these constraints. So if I can constrain the stability path to be equal across time, that has some nice properties that we'll get into later. So let's just assume for a minute that the stability path is constrained to be equal across time. And let's assume that the stability path is 0.9, okay? So that means that the correlation between those every two adjacent time points is 0.9, which is actually really, really high, right? I mean, that's some serious stability. But now let's think about, what does that mean in terms of the correlation between like the first time point and the last time point? Because again, and just think back to like our tracing rule and path analysis, this is like a complete mediation model, right? So that's really like, what's the indirect effect of SX6 or RDSX6 reading at 6 on reading 11, right? So how would we compute that if all of those paths are 0.9? Yeah, exactly. 0.9 times 0.9 times 0.9 times 0.9 times 0.9. So it's going to be 0.9 raised to the power of 5, right? Are there 5 of them there? Okay. So hold on. Let me get my little calculator out here. Do that. So I think I got enough 0.9s. I think it's like 0.59. You have enough 0.9s? I think I did. And imagine actually, what if you had 0.9 here? Somewhere here, I've got an exponent on here, right? P. Imagine you go 0.9 raised to the power of, where is my, I don't have a little raised to the power of, but imagine you go 0.9 raised to the 20th power, let's say. Well, even though between each adjacent time point, you have this really, really, really strong correlation, once you go out that many lags, the correlation between time 1 and time 20 is actually going to be very low, right? So even a really, really, really strong stability, between two adjacent time points does not necessarily imply that, it doesn't imply that like there's sort of forever stability. That's different. It's a little different from like a factor model. Let's say when we have a factor model and we're thinking about there is some factor, right? And I've got these measurement weights that are predicting, you could even fit a factor model across time, for example. You could say like all of these, let's say I'm going to make something up. Let's say I've got scores on some cognitive assessment. And I think that these cognitive assessments across time are all indicative of some like general ability factor. And I think that thing is really stable across time. I'm not saying that's true, okay? But I'm just saying like, let's say that's my worldview. So you could imagine fitting like a factor model, right? So I've got this, let's call my factor G, as kind of factor analysis was born out of a lot of that study. So let's say my general factor is predicting people's cognitive ability scores in like, first grade and fifth grade and 11th grade and adulthood or whatever. And if you think about it, then the correlation between the score at fifth grade and the score at adulthood, that model implied correlation is going to be, using the tracing rule, it's going to be like, this path times this path, right? So a factor model is going to sort of, if you think about it, you're going to expect much more sort of consistent pattern of covariation across time, whereas an autoregressive model, even when that stability is very high, what you're saying is adjacent time points are much more similar to each other than non-adjacent time points. And the more lags you go out, the less similar people are. There's kind of like a really interesting classic example of like an autoregressive process that is highly stable, but actually ends up with very low correlation. So if you look at, if you rate people's attractiveness, let's say, this is a sort of social psych kind of study that somebody did. So you rate people's attractiveness, let's say at age 18, 19, 20, and imagine you rate people's attractiveness for like every year for, say, 70 years, okay? So if you look at the rating of attractiveness from like year 1 to year 2, it's actually very, very stable, right? Very highly stable. But if it is actually kind of an autoregressive process. And if you look at like people's ratings of attractiveness at, let's say, age 18 and age 90, not surprisingly, maybe the correlation is actually quite low, even though like from 89 to 90, it's a very stable, and from 18 to 19, it's very stable. The good news about this is if you don't feel like, your ratings of attractiveness are that high, just as you get older, you're going to, like, the rank ordering gets all mixed up, so you don't have to worry about it. That's the one good thing about age. Anyway, so, but you see what I'm saying? So, like, here's this thing that, like, over, close time points is really, really stable. But there is this process where, like, that correlation is actually being dampened across time. That's what we're talking about. That's sort of that's our worldview with these models. So it's not that it's not something that's completely stable. That would be like a factor. It's not something that's like growth. We talked about growth for the last 2 weeks. It's this idea that there is this stability. The stability is stronger the closer in time. Like there is some, right? There is some prediction going on with, from time point to time point. But eventually, over a long enough period of time, that correlation is going to dampen out with an autoregressive process. Like, just imagine 0.99 to the power of 100 is going to give you something close to 0, right? So if you sort of wait it out for long enough, the correlation between the first time point and the last time point is going to be close to 0. After, again, after a long enough time point. But in the near, sort of with near time points, you could have very high correlations. They're not always 0.9. I keep saying 0.9 just as to be extreme, but your stability coefficients don't have to be 0.9, right? Yeah, the logic is the same whether or not you constrain the paths. What's different is the math is not 0.9 raised to the power of 10 now. It would be like 0.9 times 0.85 times 0.8 times 0.93 times whatever they are. But the logic of just, it's an indirect effect from here to here is the same. Totally the same. Good question. Okay, so let me go back here for a sec. Okay, so so this idea is, right, that we're really estimating the stability of some variable, some construct by regressing later measures on earlier measures. And, we sort of expect what's called a simplex pattern. Like, again, if you sort of think about what I just described, we could actually take those correlations that I was talking about and we can fit them into a correlation matrix. And that correlation matrix will follow what's called a simplex pattern, which I'll show you in a second. Okay, so I think I've said all that. Let's see. I said all that. Okay, so here's our simplex pattern. So let's assume now, let's forget about error for a minute, and let's just assume that we had like an autoregressive parameter, and let's assume it's set to 0.8 across time. So it's the same stability coefficient across time. Then the correlation between adjacent time points, so like A1 and A2, or A2 and A3, or A7 and A8, any two adjacent time points is going to be 0.8. The correlation between time points that are like, you know, 2 lags apart are going to be 0.64. The correlation between, not hot time points, but well, the correlation between variables that are at time points that are 3 lags apart are going to be 0.51, right? So we're talking about the correlation between variables at certain number of time point lags apart. And you can see here, like the correlation between A1 and A8 would actually be 0.21. So we can put that actually into a correlation matrix, right? And notice the pattern that you get. This is what is referred to as a simplex pattern. So notice that, you know, okay, we've got, again, it's correlation matrix, so we've got ones on the diagonals. And notice the first sort of off diagonal all the way down the line is 0.8. Those are our, again, they don't have to be constrained to be equal, but for the simple example, they are, because that makes the correlation matrix much easier to look at. So our first off diagonal, we have all 0.8. And then our second off diagonal, we have all 0.64, 0.51, 0.41, and so on and so forth. And actually, I guess here I went with one extra lag as compared to the last slide. So you can see that here we think we've got one more time point. So the correlation between the first and last lag is actually 0.17. But do you see that sort of diagonal banding there? So that's sort of your classic simplex pattern. And again, we're not taking into account measurement error here at all. So we're sort of assuming we're measuring this thing without error, and our autoregressive paths are 0.8. So no, the state here, state equals 1.0, that just means I'm assuming I have no measurement error. So, yeah. Simplex really means it's this pattern of correlations that we're seeing here, where this is what would be called a simplex pattern, is that you have this, this correlation matrix follows a simplex pattern, where you have like this band. Do you see? You have the band of the sort of autoregressive stability coefficients, and then, and actually you can express this. I mean, this is like perfect, right? This is like, it's like perfect simplex. I mean, you can have sort of like an approximate simplex, might not be absolute. That's part of the challenge always is like, well, simplex, or am I seeing a simplex in there or not? But like, so really, if you think about this, the general rule here is default is 0.8. Default 0.8 is equal to rho, right? That's the autoregressive parameter. So in a simplex, what we really have is this first off diagonal are rho, right? The second off diagonal is rho squared. Third off diagonal is rho cubed. Now we've got fourth power. Raise the power, sixth power, seventh power. Yeah, I mean, like, again, this is like your perfect, yeah, if it's not that consistent same value, you're not going to get something that is like this. But if you, but again, when you look at real data, so like imagine, so sometimes I look at correlation matrices before I ever do any analyses, right? And one of the things that I look for in a correlation matrix, and there are lots of things I look for, matrix, but one of the things that my eye zooms toward is like, does this correlation matrix seem to follow an approximate simplex pattern? And I can tell you, like, with real world data, it's never going to look that perfect, right? It's never going to be exactly, but like, you can look at correlation matrices and be like, it looks kind of like, I'm going to call it like an adjective. That looks kind of simplexy to me, right? Looks like there might be kind of a simplex. And that's telling you like, okay, hey, the measures that are closer together, adjacent, are more correlated, right? And then they get less correlated across time. And, you know, again, like, this is a perfect simplex. This is like, technically this is a simplex, but, you know, things can be more or less simplexy looking, right? Does that make sense? Yeah, I mean, if I, yeah, absolutely. Over growth or over factor or over, you know, other kinds of things. And that's right. If a growth, you know, we didn't talk about what the variance covariance structure of the variables would look like in a growth model. It wouldn't look like this. We could go back and kind of revisit that at some point. But you wouldn't, you're not going to get a pattern that looks like this actually. All right. So that's a simplex pattern. Perfect simplex. So pretty. All right, now let's talk about measurement error. So error can be stochastic, which is random, right? We can have just random error, or there can be, you know, systematic error, right? We know that random error in dependent variables, you know, is problematic. Random error in independent variables is even more problematic. And of course, if you think about it, you know, in these autoregressive models, all those mediators are functioning as predictors as well as endogenous variables, right? So measurement error in my mediators is also going to be problematic. So, what we would really like to do is estimate these autoregressive models with latent variables rather than observed variables, because, you know, that perfect simplex that I showed you, that again is like really only exists in my imagination, because all variables are measured with error. So even if that were the correlation between the sort of the true scores, that's not what I would see in my correlation matrix, because all of my measures are measured with error. So a quasi-simplex pattern is when you have observed variables that have some degree of measurement error, okay? So let's think about what that looks like. I'm going to come back to the... So now notice where I say state is 0.9. So error is 0.1. So here I'm saying like, okay, imagine the reliability at each time point is 0.9. Okay, so my measure is not perfectly reliable, but my reliability, let's say, is 0.9. So what would I expect the correlation between time 1 and time 2 to be if, again, let's assume the stability is still 0.8, but the reliability is now 0.9. And I wouldn't actually expect the correlation to be 0.81 anymore. 0.9 anymore. I wouldn't expect the correlation to be 0.9 anymore. 0.8, sorry. I'm getting mixed up about which is my stability and which is my reliability. I wouldn't expect the correlation to be 0.8 anymore because I've got, the measure has some degree of unreliability at time 1 and time 2. So if the reliability of my measure at time 1 and at time 2 is actually 0.9, then I would expect to see a correlation between time 1 and time 2 of 0.72, not of 0.8. So you see how the measurement error has actually attenuated the correlation between the two observed measures. So the true scores are correlated at 0.8, but the observed scores are only correlated at 0.72 because the measures are not perfectly reliable. Does everybody follow that? Does that make sense? Okay. And so again, you know, you can sort of estimate what would those correlations look like then in the presence of measurement error. And again, here I'm assuming that the measurement error or the reliability is constant across time for simplicity, but it doesn't have to be necessarily. So like here's a quasi-simplex pattern where, again, now you can see it looks a lot like a simplex pattern, right? We still see that band diagonal. But what I'm getting here actually is a different set of numbers than I had the first time, because now I've still got an autoregressive path of 0.8, but the autoregressive path is between the true scores at time 1 and time 2. And there is some degree of unreliability of measurement. That's the reliability, right? And so that's basically 10% of the variance at each time point is error variance. That's really what I mean by the reliability is 0.9. It means 10% of the variance at each time point is error variance, 90% of the variance at each time point is true score variance. Really, I want to know how well again, from a latent variable modeling standpoint, I want to know how well the true score at time 1 predicts the true score at time 2. The measurement error is a nuisance, and it's like messing up my models, right? So how am I going to deal with that? Well, I'm going to show you. Okay. So let me just say, okay, if I want to fit an autoregressive model using latent variables, I need, again, I'm saying the true score is sort of what I'm interested in modeling across time. That current state is a function of the previous state, just like we were talking about. And so we're going to model the effect of the prior true score on the current true score variance. And I'm going to do this. I need at least 3 waves of data, just like I did with the growth model, actually. So that's easy to remember. We're going to go with 3 waves again. And I'm going to fit this as a single indicator latent variable model, which is kind of cool. So it was the first time we've done that, right? So I'm going to fit a latent variable, and each of my for each time point, each of my latent variables is only going to have 1 indicator. And you remember that when we were doing factor analysis, I said to you, how many variables did I say you needed? I said, for a single factor model, you got to have 3. You can get away with 2 if you have multiple factors and they are correlated, you can get away with 2 indicators. But like, I didn't give you any kind of single indicator options, right? So we're going to have to do some tricks here to get this to work. So we've got an autoregressive factor. We're going to specify that the errors are uncorrelated with each other. That's important both in terms of getting the model to fit, but it's also important conceptually. If we're really talking about random error, then it makes sense that the random error should not correlate across time points, right? Like, that's the whole idea of this error, is like just noise, and the noise at time 1 should not be correlated with the noise at time 2, right? So we're going to say that the errors are uncorrelated with each other. Okay, now what are we going to do about these error variances? Oh, wait a minute. Before I talk about the error variances, I skipped a bullet there. Each factor is has just a single indicator. So remember when we use a marker variable strategy, right? What do? We always set the first path equal to 1. So think of every variable, because we only have 1 measured variable for every latent variable. Think of it as like all of our measured variables are going to be marker variables. So we're going to constrain the path from the latent variable to the observed variable to be 1. We can't freely, again, if you stop and think about what we're trying to do here, of course, we cannot freely estimate that path. We're going to constrain that path to be 1. So we've got a latent variable. Third variable has an error. interested in autoregressive path, not among the observed variables, but call this one, call that one B2. So I could, could constrain B1 and B2 to be equal, right? But I don't necessarily have to constrain. Yeah, talk about why that might be nice. While, but like for now, just know if they don't know. Okay, so now, actually going to get this model to be identified. Well, okay, so you got it. Variable 2, actually, I can borrow information a little bit. I'm trying to identify these parameters in my mind. Right? Like, yeah, there's only a single, but like, again, I can sort of, just like when we have a factor model, remember I said we can get away with 2 indicators that have a correlation between the factors. That's because I can kind of borrow that information about the correlation between factors. That like gives me some more information with which to identify the element of interest. So like when I'm sitting here in the middle of this chain, I can kind of lean on my friends on either side and like use them to give me some information to actually identify those covariances in the middle, those elements in the middle. But I don't have that luxury at the end of this autoregressive chain. So like, right here, I don't have 2 friends to lean on. Here, I don't have 2 friends to lean on. I have one side, and that's not enough, really. So what we do to identify this model is that we need to constrain on me. Okay. We need to constrain the error variances at the first time point, the second time point to be equal to each other. So I need add E1 to be equal to the variance of E2. And I'm going to have to do the same thing at the other end of the chain. So I'm going to have to constrain the variance of E2 to be equal to the variance of E3. Now, in this 3, with only 3 time points, if you think like logically, what does that mean? If I say that the variance of E1 has to equal the variance of E2, and the variance of E2 has to equal the variance of E3, then I'm really constraining them to all have the same variance. So with this 3 time point situation, you must constrain all of the variances to be equal to each other. So really what I'm going to do is constrain the variance of E1 to equal the variance of E2 equal the variance of E3. Okay, what does that really mean then? Let's think about what we're saying when we constrain those error variances to be equal to each other. I'm really saying the amount of measurement, like the amount of like measurement error variance, right? That sort of part I can't predict. That measurement error is constant across time. Which in some sense kind of makes sense, especially when you're talking about like it's the same variable measured across time. And so I'm saying like there's going to be the same amount of measurement error at time 1 as there is at time 2, and there's going to be the same amount of measurement error at time 2 as there is at time 3. I have to make that assumption in order to identify this model. So like if that feels like it's not a reasonable assumption to make, okay, then you got problems, right? But often that really is a reasonable assumption to make. So let's just say that these are test scores, imagine, across 3 years, right? And I mean, generally like the amount of measurement error in the test is, I mean, do we really expect there's going to be like more measurement error in year 2 than there is in year 1? Not necessarily, right? I think the reliability are going to drop time. So that's really what this is saying. So with 3 time points, we're going to have to set all of the error variances to be equal to each other. If we have more than 3 time points, we have to set the first and second to be equal to each other, and we have to set the last and the second to last to be equal to each other. So like if we had 4 time points, we could at most estimate 2 error variances, one for times 1 and 2, one for times 3 and 4. For this reason, though, it is fairly common to specify equal error variances across time. Again, it doesn't have to be, like you can look at whether that's a reasonable assumption or not, but in many situations, it feels like it's a reasonable assumption to say the measurement error is going to be equal across time. And then in that case, people would actually set all of the error variances to be equal to each other, even if they have more than 3 time points. But you don't have to. But you do have to if you've got 3 time points. And if you've got more than 3 time points, you've got to do it. Oh, yeah. So you could. I mean, again, I suppose it probably depends. Like if I really have like 70 waves of data, I could constrain all those error variances to be equal across, 70 waves of data. Although my guess is like, such a big model, maybe I find that doesn't fit well. I mean, there's a little bit of that too. Like, but yeah, you could. You absolutely could. And you could also test it. Like, so you could constrain them, and then you could free them, and you might discover. I mean, if it were a really, really long autoregressive process, you might discover that there's a different amount of error at different points in that process. But you could like block it and say like, I think the error variances for the first decade are going to be equal to each other. I think you know what I mean. You could do that too, and say like, I'm going to E1 through 10 are constrained to equal E11 through 20. I mean, I'm making that up. You would have some sort of conceptual reason for 1 to 10 and 11 to 20, but you could have sort of blocks too of measurement errors equal to each other. But you're going to have to constrain at least some of the measurement errors to make this thing work. Yeah. Systematic error would look like error that isn't related. I mean, it's like not, yeah. Oh, do you mean like an example or like an, let me think with it, like one observation across. So maybe something, this is tricky because I want to like come up with something that's systematic. Systematic error could be something that happens at a couple of time points that doesn't happen at other time points, that causes those 2 time points to be more correlated with each other than would be predicted by the autoregressive trend, but is still not really about the true scores. So well, a Rader effect is a really good example of like some systematic error variance. Although it's not a great example here because we don't have any Raders, but yeah, something like a Rader. I mean, there are lots of different kinds of variance that we could have, right? There's like totally random error. There could be systematic error like, well, again, this doesn't really fit for longitudinal, but Raders. What about teachers? Like right now I'm doing a study where we're looking at how much does a teacher influence the rating that is given, right? And there's actually quite a bit of teacher level variance. So you would want, like it's a teacher rating of a student, you would want the teacher rating of the student to be a function of the student, not a function of the teacher, right? And the degree to which it's a function of the teacher, again, is not good. Sort of, it's systematic, but it's also not like the true score variance that I'm interested in. All right, yeah. Oh. Yeah, can you? Should you? mean, you can do anything you want, I suppose. But I mean, you want these to be, I mean, they could be different in the sense that, for example, you could imagine something where you've got an achievement test and maybe kids aren't taking the same exact questions, but like they're all on those tests are on a common scale. Like that's totally fine. But like if you start switching, like let's just say you're like, oh, I measured academic self-concept with Marsh's inventory for the first 5 time points, and then I switched to this other inventory for the last 5 time points. I mean, that's dangerous, right? Because I mean, I would say that is an example of sort of systematic error variance, right? That you're introducing some variance that isn't maybe about the true score. It is going to be systematic, but it's also error. So yeah, you wouldn't want to do that. And the other thing that I didn't mention, I know I have it in the slide somewhere, I should have said it strongly up front, is all of these models, the way that I've sort of, if you think about it, I'm saying that the correlation is sort of equal between, you know, like a lag 1 correlation, right, is, I mean, they may not be equal across time because I could let those, but well, if you think about, I'm saying like there's some correlation at this lag. I'm really saying this lag is some amount of time. So for these models to work, you really need the time lag to be equal across time. I mean, technically, you can get away with fitting these models if the time lag isn't equal across time, as long as you don't constrain those stability coefficients to be equal, because then you can kind of allow those to vary as a function of how long the time is. But like really, when we do these autoregressive models, we really want to be having, we really want the time lag to be equal across time. And there's actually like a trick that you can use with phantom. Have we talked about phantom stuff yet? Oh, we're gonna talk about phantom variables today, but in a different context. There's a trick you can do. You can use phantom variables actually to, if you don't have equal time lags, you can actually introduce a phantom variable to sort of get something like an equal time lag. So I can show you sort of how that works later today. But this is important. We are making the assumption that, like, you know, if I were doing that thing with like attractiveness, I'm measuring it like, let's say every year or every other year, whatever. It's not like between time 1 and time 2 is 1 year, and between time 2 and time 3 is 5 years. Because if you think about it, if a lag is 1 year, I mean, just do the autoregressive thing. Like if it were really 5 years, then the path should be, I would expect that path to be rho raised to the power of 4, not rho to the first power. That's why I say, like, you can kind of get away with unequal time lags if you don't constrain the stabilities to be equal to each other. But a classic autoregressive model, you know, does have equal, you know, sort of equal time intervals. And we often want to be able to constrain the stabilities to be equal to each other. So we really want those equal time. Does that make sense? Okay. So we did the quasi-simplex pattern. Okay, here's a pretty quasi-simplex pattern. Here is my drawing. Here's a drawing for an autoregressive model. So I would have to constrain these two to be equal to. So at most, I'm going to be able to estimate 2 error variables. So let's think about this for a second and think, like, how many parameters can I actually estimate? Should have done it. To the 4-wave model. How many parameters am I estimating? How many degrees of freedom do you? Well, let's start with our knowns. That's easy, right? I've got 4 variables across time, right? I've got, so my covariance matrix is 5 divided by 2, 10, right? So there are 10 unique elements in the variance covariance. Obviously, 10 is going to be the max number of parameters that I could possibly estimate. How many parameters am I estimating? Well, here we're not constraining. Okay, so how many paths am I estimating? Okay, how many variances am I? I'm not estimating any correlations, right? How many variances am I estimating? Yeah, one exogenous variable variance. Okay, what other variance? 3 endogenous, right, disturbance variances. Okay. Yeah, and 2 at most, right? Like assuming that I do with 2 different ones, 2 error variances. Okay. Anything else I'm estimating? So what have we got? 9. Got 9 parameters. And remember, I said we could have at most 10 because we've got 10 elements for our covariance matrix. So 10 minus 9 equals 1 degree of freedom. So this is actually a 1DF model, right? If I constrain the parameters for paths to be equal to each other, then it would be how many degrees of freedom? I constrain path P1. Yeah, exactly. Equals P2 equals 3. Then I'm estimating 1P instead of 3P, so I pick up 2 degrees of freedom. So if I did that, this would be a 3 degree of freedom model, right? How about if I only had, think about this for a second. What if I only had 3 waves? Knock this out for a second. Here we go. So imagine I said 3 was our minimum, right? So I've got 3 waves of data. How many knowns do I have? 3 times 4 divided by 2 is 6. Right? So 6 unique elements in the variance covariance matrix. So I can't go above 6. How many parameters am I estimating in this model? Well, I still have 1 exogenous variance, right? I have 2 disturbance variances. I have 2 paths. Yeah, assuming we're not constraining them to be equal, I have 2 paths, right? And how many error variances? 1, because remember, I'm going to have to sort of yoke these all together. So I've got 1 error variance. Okay, so 2 plus 2 plus 1 plus 1 is 6. So I'm actually estimating 6 parameters. 6 minus 6 is 0. So actually, interestingly, this model is just identified. So if you were to fit this model, you can get parameter estimates. You're not going to get a chi-square or degrees of freedom. It's a 0DF model, so you're not going to get a chi-square. And what that really means is you can use these 6 parameters to exactly, your model predicted variance covariance matrix will exactly reproduce the variance covariance matrix because you have as many parameters that you're estimating as you have, you have as many knowns as you have unknowns, or unknowns as you have knowns. So in this case, this is a just identified model, which could, of course, be compared, let's say, to a 1DF model where we constrained P1 equal to P2. If we did that, then the model has 1 degree. Only estimating 1 path instead of 2. That make sense? Okay. All right. Right. So in terms of identification, which we just talked about, we need at least 3 waves. And with 3 waves, if I allow those stability coefficients to vary, the autoregressive paths to differ, will be just identified. we'll have 1 degree of freedom, as I just said, if we force them to be equal. We are over-identified if we have 4 or more waves. And as I said, the residual variances and stabilities are identified for the middle waves, but we've got to constrain those error variances for the first and second time points to be equal, and the last and next to last time points to be equal, no matter how many time points we have. Like 100 time points, we still need to do that yoking of the errors at these sort of ends of our autoregressive model. Yeah, just to identify it. Just to identify it, because otherwise I'm not going to actually be able to identify. I'm not going to be able to identify some of those parameters there at the end. Well, no, actually, you picked up degrees of freedom with more waves. You do have more unknowns, but you also have more knowns. Because remember, you've got 5 waves now, you've got 5 variables. Yeah, there's no, no. That's really just a function of, again, like, we're trying to do a single factor model. It's really, that's what it's about. It's about having like a not single factor, single variable, single indicator latent variable model. It's right. So in order to actually be identified, we have to yoke those error variables, the first and second time point and the last and next to last time point. No matter how many time points you have, you're always going to have to do that. Okay, we already talked about the 3 time point. So why do you have to constrain those variances to be equal? Again, think about it. At time 1, you're trying to estimate a latent, you think about it, at time 1, right, you're really trying to estimate the latent variable variance, and you'd be trying to estimate the error variance with only 1 variable. Like, how are you going to do that? Like, it doesn't make sense. How can you possibly like take just this 1 observed variable, and if that's all you really know, how are you going to be able to break it into this, latent variable variance and this error variance, like, without some other information? So that's really the problem. Like, at time 1, you're trying to get this latent variance and this error variance with only 1 piece of information. In the middle time points, again, you're borrowing information from the prior and subsequent time points, as long as the variables are related to each other. Now, where this would break down, by the way, is if you didn't actually have an autoregressive process. If those autoregressive paths ended up being 0, so like you fit, you've got the model, you fit the model, but there really isn't an autoregressive path there, it really is 0, then you're going to be what's called, again, empirically under-identified. So like theoretically it should work, but given the fact that those autoregressive paths are 0, then you're not actually going to be able to estimate this model, because what you would have is like a whole bunch of single indicator latent variable models sort of standing next to each other, and there'd be no way to actually identify that. Yeah, M+ would give you an error and be like, I can't do this. Then I mean, that's highly unlikely to happen, because again, you're talking about the same variable across 2 time points. Like, it's a little weird, but technically, like, that's what it would mean. All right, I already said this a million times. So, okay, so theoretically, if you had, let's say, more time points, you could potentially estimate like second order autoregressive models. We're really not going to do anything with this, but conceptually, what a second order autoregressive model is, like, what you're saying is, okay, variable at time 2, no direct effect, the variable at time 1 on the variable at time 3, right? The first order autoregressive is saying that the only, the total effect, let's say, latent variable 4 on latent variable 1 on variable 4 is just totally completely mediated through those first order paths. Right? There's no other way. So, for autoregressive, direct effective latent 1 on 4 is 0. The direct effective latent variable 2 on 4 is 0. Okay? Second order autoregressive model, I'm saying, okay, you know what? Actually, maybe there is a direct effect of the variable on the first time point on the variable at the 2 lags away. So second order autoregressive means you're fitting a direct effect for a lag 2 as well as a direct effect for theoretically. You could have a third order autoregressive. Obviously, these get increasingly less parsimonious. And I would say also, once you start getting into this, then those are places where you may actually need to, for identification purposes, you may change the parameters, stability parameters to be equal across time. For example, we saw that we had 1 DF, right, for our 4 time point model. So we couldn't actually estimate this second order model and allow all of these paths to freely vary, right? Because we'd be adding 2 paths, and I think we saw we only had 1 DL, right? So we'd have to constrain, at least we'd have to either 2 to be equal to each other. We'd have to do something to pick up some degree of freedom. But this is what, if you hear people talk about a second order autoregressive model, it just means you're allowing direct effects for lags that are 2 away from each other, not just lags that are 1 away from each other. The question you should be asking yourself is, why would you expect that, right? You really need to have, you really need to be able to conceptually make some sense of why. So again, let's just think about this. This would be like saying, let's say this is, say we've got 3rd grade, 4th grade, and 5th grade reading scores for a kid, right? And so I'd be saying, like, for 4th grade reading scores, predict your 5th grade reading scores. That's lag 1. And then I'd be saying, after controlling for your 4th grade reading scores, your 3rd grade reading scores actually help predict your 5th grade reading scores, again, after controlling for 4th grade. So there's some direct effect there. There's some ability for 2 years ago reading to predict where you are now after controlling what your reading score was last year. Now, again, I'm not saying that's not possible. Like, you conceptually may have an example in your own research where that makes sense, but often it doesn't, right? And it's like, you really have to think about, why would you expect a second order autoregressive path, right? That's sort of the onus is on you to make, sense of that. You should not just add second order autoregressive paths just to like make it fit better, right? And then be like, oh yeah, okay. Now let me make up some story about why that makes sense, right? Yep, yes, and then there, yeah. Well, again, I think the growth curve model is really a very different model of sort of the variances and covariances. But, I would be hard pressed to give you an example of where I think a second order autoregressive model makes a lot of sense. And I've definitely done some, I can remember many moons ago now, probably 15 years ago, I was working with somebody who gave me some data and we were fitting, like a cross-lag panel model. And it was really weird. It didn't fit well. And it's because there was this huge, like, lag 2 path, not consistently, like in one part of the model. It was lousy, totally determined by the fact that, like, the correlation between 3rd grade and 5th grade reading, the correlation between 3rd grade and 5th grade wasn't adequately by the model. But the other correlations were. So, like, the correlation between, and when I looked at the actual correlations, the correlation between 3rd and 5th grade reading was like actually higher than the correlation between 3rd and 4th grade reading, or the correlation between 4th and 5th grade reading, which is really weird. Like, I could not think of a substance. Now that's what, I mean, again, that's just like the regular old correlation matrix told me that. So I went back to the researcher and I said, like, honestly, what I said is, are you sure there isn't a problem with your data? Because this just doesn't make any sense to me. I can't think of a reason why 3rd and 5th grade scores on the same assessment would be correlated more than 3rd and 4th R or 4th and 5th R. Like, that just does not conceptually make any sense to me. She got really mad at me. And we never finished that project. But anyway, I digress. Well, sure, but for one student, but remember, we got a whole slew of students. This isn't just like, this isn't single subject. So like, yeah, but is that really going to happen with a couple hundred students? I mean, but maybe you can think of an example where like, or yeah, like maybe the school, I mean, okay, so maybe the school, maybe it's everybody comes from one school and the school did, you know, like they had this new program and then they dropped it for a year and they brought it back or something. Maybe, right? I mean, so like, and if you have that information, then that's what I mean. Like, then you could be like, oh, actually, I happen to know, I have insight into this process. And I know that even though this is unusual, in this case, it does actually make conceptual sense. But in the case that I'm talking about, the person was just annoyed with me. And I was like, no, my data are fine. I don't know what you're talking about. But I was like, so, yeah, so maybe, so sometimes it might make sense, but you know, it certainly isn't this is not our go-to model. First order is much easier to make sense of. Okay, we take a break pretty soon. So let's just see where we are here. I want to get to where, these are the model equations, which I think I can skip over that slide for right now. Oh, there we go. Okay. In terms of, I do want to say something about this. So remember, in this model, we have both disturbances and errors. So that's a cool thing about this model, this latent variable model. So, you know, and if you think about it, again, if you think about it using the tracing rule, the errors, they're kind of stuck, right? The error, it only relates to the indicator at its time point. Like if you think about the tracing rule, right, you can't go, like you can go forward sort of from the error to the score at time 1, and then you're stuck, right? So the error really does not, there's no way for the error to relate to subsequent errors or to subsequent scores. Do you see that? Like there's, right? It's like, this is it. This is just, it's truly error. It's truly time specific stuff here. Now, think about the disturbance. That's not true. The disturbance, right? The disturbance, this disturbance, B1, the piece of latent variable 2 that is not explained by latent variable 1, that's what a disturbance is. It's the unexplained piece of latent variable 2. But sort of think about how this plays out then, subsequently, so the disturbance is something happens. Like it's some random shock. Something happens to the system. And that disturbance, though, is going to be related to latent variable 3, right? Because really, here we're saying, you know, how does latent variable 2 predict latent variable 3? And latent variable 2 is broken into 2 pieces. The latent variable 2 is the piece of latent variable 2 that's by latent variable 1, and the piece of latent variable 2 that's not explained by latent variable 1. That's what this disturbance is. But both the explained piece and the unexplained piece are, that those together make latent variable 2, and latent variable 2 then predicts latent variable 3. So the point here is that, you know, any of this error variance is sort of, it's contained. Right? Contained in the bottom of the model. It's not going anywhere. This, you know, it predicts the indicator at that time, and that's it. And there's no way for like any of this error to like move through the model. But that's not true with the disturbance. The disturbance absolutely does relate to subsequent, not prior, but subsequent time points, right? So the disturbance here is unrelated to latent variable 1. Definition of the disturbance, right, is like it's the unexplained variance. So clearly it's not related to time point 1's latent variable, but it is related to time point 3's latent variable, time point 2's as well. It is related to time point 2's latent variable, time point 3's latent variable, time point 4's latent variable. So, again, we can sort of, so we have these two different kinds of residuals. One is really just capturing this time-specific error variance, and the disturbance is really capturing like these things that happen, right? Things that happen that might then influence subsequent stuff. So like a random shock that might disrupt the correlation between DV1 or LV1 and LV2 might be that the school implements a new system and some kids respond to it better than other kids, right? And so that sort of, or whatever, that disrupts, that's sort of like a disruptor, but the effect of that sort of shock then does influence forward. It's not just like random measurement error. It's something that happens. Like, and if you think about it in our lives, there are all kinds of like random like we go through life and right, there are all kinds of random shocks that are happening to us all the time. And I mean, I'm saying random, but like there's something, like a really gory, morbid example. Like, you're walking across the street and you get hit by a car, right? It's like a random shock, but it totally affects your system moving forward, right? So like it was this random event that you weren't expecting, but you carry forward the impact of that. It's a horrible example. It's really gory, as I said, and disturbing, but they could be good random shocks too, like you win the lottery. We'll do the happier one. But like those things, even though they're sort of these like events that might be happening, some people are having these things happen to them, some people aren't, or whatever. There are these things, or maybe it's happening the whole system, but these things that are happening, these random shocks, they aren't just measurement error. It's not just like time-specific measurement error. It's stuff that's happening that's disrupting the system, but it's like also you're carrying that disruption forward. Does that make sense? Okay. Which again, I think the ability of these models to kind of separate those two things out is awesome. All right, so this whole slide, which I will not go through right now, but you can look at, it just shows exactly how, how latent, how to predict latent variable 4 as a function of latent variable 1 and its disturbance, and the disturbances for 2 and 3. So you can kind of follow along with that. I will not do that today because we're running out of time, and I definitely want to get to our example. And I want to give us a break in just a sec, but I kind of want to give us a break and come back to the example. So we've talked about this idea that the stability, the standardized regression coefficient that we get, that B path, the standardized B path is what's used as a measure of stability. The stability could be, again, we could constrain those stability coefficients to be equal across time, but we don't necessarily have to for identification purposes. And then there's another coefficient that's really important, and that's the reliability. And the reliability is actually the squared multiple correlation of the measure. So if we were to go back to, well, you will see it in the M plus output, but basically, let me go back here for a second. So, imagine we're going to get what proportion, we're going to get an R squared for this measure in M plus, right? Each of these measures. And that's going to be like, what proportion of the variance in that measure is explained by the latent variable? And that's what I'm talking about when I talk about this R squared. So note, though, that the stability is in an R metric, like a path coefficient. And the reliability is in an R squared metric, like an R squared measure. So just kind of keep that in mind. So the reliability is the proportion of the variance in that indicator variable that's explained by the latent construct. And we'll get those reliabilities from our output. Okay, I am going to stop there. We're going to take a break, and then we're going to come back and do some M+ stuff and talk a little bit about stationarity too. Take like till 10 after. I just realized something. Hey, Antonia, could you see the slides that I was showing?
I can't, but I've just been following along with my download of the slides.
Oh, no! I just realized as I came back in and hit record again that, like, I don't know if I hit share screen.
Oh, sorry, I should have told you. I was
am
following
so
along
sorry.
just fine.
You should have
That's
said
okay.
something, but maybe you did and
I'm
I couldn't
sorry.
hear you. Oh. The first half of the recording does not have the screen. I am so sorry. It's bad.
It was pretty easy to follow along.
Well, I appreciate your saying that. Thank you.
Slides.
Okay. Well, I won't forget that this time. How about that? So let me see here. I did hit resume. I remembered to do that. And that's when I remembered that I had not. Okay, so let's see. Content. To be the screen, right? Okay, can you see my screen, Antonia?
Yes, I can.
Okay, that's awesome. Okay, so, oh gosh, you know what yeah, we didn't talk about one other little thing. Let's go through the first couple models and then we'll talk about phantom variables. We didn't talk about phantom variables yet. But let's do a couple models first. Okay, so if you go into the courses folder, week 9, you will find a whole set of, these are the right ones? Yeah, those are the right ones, right? Yes, they are. Okay. You go into week 9, you will find a whole set of autoregressive models. So let me just open the first one and then we can talk about it. Week 9 autoregressive models. So we're going to start with model 1. Oh, and actually you should also have output. Did you give out the output? Okay. So you should also have output, which is set up a little bit differently this time. So here's the thing. So for our autoregressive models here, we're using this CMT data, and so it's school level data. So it's school reading scores. So like the school mean reading score from 2006 through 2008. Sorry, 2008. So that's what 08 is through 2013. So we have multiple waves of data collection. And again, this is school reading scores. And I would argue that, like, if we were looking at kids' reading scores, let's say from 3rd to 4th to 5th to 6th grade, then I think a growth model would make a lot of sense, right? I don't know that an autoregressive model would make as much sense, although, you know, we could compare them. But here we're really talking about like school average reading scores in 2006 and school average reading, or 2008, sorry, school average reading scores in 2009, school average reading scores in 2010. You wouldn't necessarily expect to see, I mean, you might hope, but you wouldn't necessarily expect to see those reading scores at the school level grow over time, but you would kind of think that schools that have better reading scores in 2008 are probably also the schools that have better reading scores in 2009, right? And the schools that have better reading scores in 2009 are probably the schools that have better reading scores in 2010, et cetera. So for this, we're going to fit an autoregressive model. Okay? Yes. Yeah, you don't have to have a means structure. You don't have to have means. You could just use a variance covariance matrix to fit an autoregressive model. And that's a difference actually from a growth model. You can't fit a growth model unless you've got a vector, if you've got to have raw data or you've got to have a vector of means. But for an autoregressive model, all you need is the, the variance covariance matrix or the correlation matrix and the standard deviations. And in fact, I think in the homework, I think the homework uses a variance covariance matrix, right, Jocelyn? So one of the things that I made note of in the homework, so it says this explicitly on the homework, but I'll just mention it again here, is so here we're using raw data. And so there are places in my code here where I may actually make reference to the means. But like you do not want to use anything with brackets in the homework because it doesn't have means. And so like, because of that we don't input any means because it's just a variance covariance matrix. If you have any brackets whatsoever in your input file, and plus it's going to be like, I can't deal with this, right? So make sure you don't, if you only have a variance covariance matrix, just make sure you never refer to means and intercepts. It's a covariance matrix. It's a covariance matrix. There are no means. So I've had that problem in the past because like in some of this, maybe not here, but somewhere in one of these models, somewhere I think there was a line that just was like bracketed that just basically said, it didn't mean anything. It was just freely estimating the means. It didn't need to be in there, but it was in there. And it threw people off for homework because they kept trying to put the bracketed means in there with a variance covariance matrix. And you can't do that then. You can't. You could, like, it was no harm, no foul with the raw data, but like that'll totally mess you up if you don't have means to model. So, okay. Like right now we don't have any, oh yeah, here they are. Here are the brackets, yeah. So this right here, all that says is really estimate the means for schools 8, like school reading 8 through school reading 13, which I don't actually have to have in there. Like, I don't really need that line, but it's in there and it doesn't hurt anything because it is going to do what it's going to do. It's going to do that, whether I have that line in there or not. So it really doesn't matter in this particular setup, but it will matter if you put that line in your homework, guaranteed it will not run. So don't put anything with brackets in your homework because you don't have any means. Yeah. This line of code is just, just says means, like we're estimate the means and means and intercepts for these. And you will, you're going to get, you always have sample means, you're going to get model predicted means. But the reality is that you're going to get the same thing whether or not you have this. It's just like you could have a line in your code that says, well, this would be a bad example, but like, well, I could put something here. Like I could put, I don't have a latent variable. But like I could put a line of code that makes references to all of the variances for all the variables. So like I could have, let's just say I didn't have the disturbance. Yeah, this constrains the disturbances to be equal. So like if I don't have this, okay, right now I have a line of code that's just saying like variance of this, but you're always going to estimate, like by default, you're always going to estimate variances for all of your exogenous and endogenous variables. You're going to estimate a variance for an exogenous variable. You're going to estimate a disturbance variance for an endogenous variable. So like, if I take this line of code out, it's not actually going to change anything. It's just saying is like variances. And just like that, all this is saying is means, which again, by default, the model is going to estimate means and intercepts. So neither of those actually have any effect. Now that's not totally true with model 1 because I was actually constraining the disturbance variances to be equal across time. So, now I really do need that line. But like, if you make reference to variables without brackets, you're just making references to the variances of the variables, and with brackets, you're making references to the means or intercepts of the variables. And like, you're always going to be estimating those things. So like, I mean, unless you're not, in which case you have to say you're not. So they don't really do anything. So sometimes I put them in, sometimes I don't. All right. Often they're there because I was doing something to constrain them and then I stopped. All right, so anyway, here we are. So this is our model. Our first model that we're going to go through really quickly is just an autoregressive model using observed variables. And remember, I said we really want to use the latent variables. We want to account for measurement error, but I want to run through this model so that you can see what the fit looks like. And we can see the parameter estimates, and then we can compare it to our latent variable model. And I think you're going to see that the latent variable model looks a lot better. So let's do that. And so you can see, like, this is real. Oh, here's a little trick. Here's a nice little piece of code that you might like. So you see that I said, instead of saying like school reading 9 on school reading 8, school reading 10 on school reading 9, school reading 11 on school reading 10, what I said is school reading 9 through 13, pawn, which is peon, paired on, is really what it is, pawn, school reading 8 through school reading 12. And that P is like going to pair the first element of the series, like before the pawn, with the first element of the series after the pawn. So if I say school reading 8, what I said there, that's really saying school reading 8 on school reading, or sorry, school reading 9 on school reading 8, school reading 10 on school reading 9. But it's a much more compact way of saying it. And given what we're doing with autoregressive models, this is kind of a nice little trick. You can, there's also a P with, so you can do that with correlations as well. Like imagine you wanted to correlate like, you know, variable 1 with variable 2 and variable 2 with variable 3 and variable 3 with variable 4 and variable 4 with variable 5, but you didn't want all the, you know, so you could say like variable 1 through 10, you know, P with variable 2 through 10 or whatever, you know. So you can just basically do that so that it'll be like 1 with 2, or I guess it would be 1 with 1 to 9, P with 2 to 10 is what you would do. So it'll be 1 with 2 and 2 with 3 and 3 with 4 and 4 with 5. And so it's always taking just like, you know, each of the elements of the series. So anyway, that's kind of nice. It might save you some typing. That's really the only new thing here. So that's what I'm saying. So that's how I've written my autoregressive paths here. Just to all of them with each other, then you're going to do, yeah, I mean, well, it would be like all with all, right? Yeah. Okay. So, which luckily, often by default, we get all of the correlations, so we don't have to worry about it too much. But so, okay, here we go. Let's run this model. I don't think I need to save any changes. Okay, that didn't take very long. And you can see, oh, I should make this bigger, right? Change font. Okay. All right, there we go. So if you look on your output, this should match. Here we go. We've got a chi-square of 199.324 for the first model. And this is the one that is constraining all the disturbance variances to be equal. Now let's take a look at our model results. And really, in this case, I'm going to be more interested in my standardized results. So let's scroll down to my standardized results and see if we can make sense of this. Okay. So again, this is an observed variable. It's not latent variable, but you can see that these are my stabilities. I did not constrain them to be equal across time. But what do you notice? They are fairly equal. That's the first thing. Yeah, actually, the standardized coefficients are fairly equal across time. So constraining them to be equal might not be such a crazy idea. What else do you notice, though? They're equal and they're, yeah, I mean, that, saying that that they're significant is such an underwhelming response for coefficients like that. Like, really, if that's all you can think to say about something that's that close to 1, like, yeah, it's statistically significantly different from 0. That is true, but it is so much more than that, right? I mean, the interesting question would be, are they statistically significantly different from 1, right? That would be a more interesting question, but we don't actually get those p-values. And they would be, by the way, they would be statistically significantly different from 1, but like, they're enormous, right? They're super high. So like, from a stability perspective, wow, no, again, think about this. Knowing how a school did in 2008 predicts almost perfectly where the school is going to be in 2009. It's not perfect, but it's awfully high. And the same is true from 9 to 10 and 10 to 11, 11 to 12, right? And again, remember, these are with the observed variables. We haven't like dealt with measurement error issues at all here. So these theoretically should be downwardly biased because they're, because we haven't dealt with the measurement error, right? So if these are downwardly biased, holy crow, what are we going to see when we use the latent variable model? Okay, but anyway, I digress for a second. So here are the residual variances, which are super small. Again, this is standardized. So that's really, these are really 1 minus r squared, right? This is the proportion of variance in these reading scores that is not explained by the prior time point. And you can see it's like 8%, 8%, 9%, 8 or 9%, right? And so now look at the r squared, which is going to be, so above here, this is just 1 minus r squared in the standardized. This is r squared. So you can see 0.919 plus 0.081, that gives us 1, right? So here are the r squareds, which remember I said are like our reliabilities. So these are the, well, actually, I take that back. They're not our reliabilities yet because we're not in the latent variable modeling framework. Scratch that. Because we have, remember, this is the observed variable. So what we have actually, we aren't able to yet partition out between the disturbance variance and the error. Hold that thought. They're not our reliabilities yet. But they are, but what it does say is that we can explain 92% of school reading in 2009 with school reading in 2008, right? So we can explain almost all of the variance in each of the subsequent time points with the prior time point. All right. So in some, and again, in some sense, this is, we can't separate out yet because it's not latent variable. We can't separate out the reliability from the, like the disturbance variance from the measurement error variance. But when I look at this, what it tells me is that the combination of the disturbance variance and the measurement error variance is, both of those put together, very, very small, right? Because I can explain 92% of the variance in each of these variables, like in the subsequent variable with the prior variable. And if I'm, so that remaining 8% in the observed variable framework is a mix of measurement error and disturbance. So in some sense, like either we have a perfectly reliable thing and we can explain, and we have a disturbance variance that's basically 8% of the total, or we have something that's reliability is about 92%, there's no disturbance variance whatsoever, or something that's in between, right? It threw me off because they're so high. I'm like, oh, these must be our reliability, but they're not. It's just, they're just super high. So, with me? Okay, how's the fit? So we can interpret those parameters, but how's the fit? The fit is, what would you say about the fit? I agree, right? We have 14 degrees of freedom and the chi-square is 199. And again, like just to sort of, gestalt sort of rule of thumb thing, we would really like the chi-square to degree of freedom ratio to be, and we'd really like it to be 1, right? That would give us non-significance. But like, if it's 2 or 3 to 1, I mean, okay, but like this is actually over 10, this is like 14 to 1 or something, right? That's huge. That's no good. That's no good. And my RMSEA is horrible. And my CFI and TLI, they don't look so bad, but really, But really, this is not a good fitting model. So you might think to yourself like, oh, well, maybe it's really a bad fitting model because I constrained those disturbances to be equal across time, right? Maybe that's my problem. So we can unconstrain those. 9, 10, 11, 12, 13, right? So now we are unconstraining those disturbance variances. So instead of estimating one disturbance, what? Oh, sorry, yes, I can. This is going to be model 1B. Yeah, I've just done it on model 1A, but if you open model 1B, you're going to see this. No, you have, if you look at the first page, you'll see the chi-square and df for 1A and then 1B right below it. You see it? No, I know. I was trying to be compact. You see it? So like 1A was like the 199, and then you're going to see 1B. And I think I might have only given you the output for one of them, but okay. So now let's go ahead and wait. I got to make this bigger. So hold on a sec. Change font. Choose font. That's better, right? So now I just took off that little constraint. So how many degrees of freedom am I picking up? I'm sorry, getting rid of. How many degrees of freedom am I getting rid of? Am I using up? Yeah, 4, because, wait a minute, hold on. 9, 10, 11, 12, 13, yes, 4, right? Because instead of estimating 1 disturbance variance, I'm now estimating 5 disturbance variances. So I'm using up 4 degrees of freedom to do that, right? I'm estimating 4 additional parameters using up 4 degrees of freedom. So let's run that. Yeah. Okay. And what do we see when we do that? Let's go to the chi-square, because that's our first question. Like, okay, so now we went from 14 degrees of freedom to 10, which makes sense, right? And the chi-square did go down to about let's call it 140. So it did go down by almost 60 points, but it's still like not a great fitting model, right? It's a pretty poor fitting model. And I don't think you're going to see that our parameter values of interest did not change that much. Let's look at our standardized. You can see those look very similar. The standardized path coefficients, the residual variances look very similar. But one difference is actually the residual variance for 11 is a bit bigger than the residual variances for the others. So for it's sort of split, but generally speaking, didn't make too much of a difference. Okay. So now let us go to our latent variable model 2, AR latent scores. Okay, so this is where I'm going to do the single indicator latent variable model. Right, and so let's take a look at this. So first thing in my model statement, I'm saying, reading 8 is my latent variable. That's what I called it. Reading 8 is measured by school reading 08, which is the observed variable, right? And so I literally it just looks like factor, the factor analysis, but I only have one observed variable per factor. And again, I don't have to say that that's the marker variable. By default, M plus is going to constrain the path to be 1 from read 8 to school read 8. Okay. And then here, instead of looking at the path, instead of using the observed variables, now I'm looking for autoregressive pathways using the latent variables. So read 8 through read 13, those are my latent variables paired on, read 9 through read 13 are my latent variables paired on read 8 through read 12. Okay, and then remember to pull this off, I'm going to have to constrain the first and second error variances to be equal and the last and next to last error variances to be equal. And the way that I actually chose to do this just based on what I saw on the last set of output, where I saw read 11 looked really different in terms of its residual. Now that was residual variance and not error variance, but because read 11 looked very different, I've decided I'm going to let read 11 do its own thing. So I've constrained read 8, 9, and 10 to be equal and 12 and 13 to be equal. And I'm allowing the error variance for school read 11 to be different. I mean, again, there are a lot of different ways you could sort of parse this up, but what you would minimally have to do, so like I could have not put read 10 in here. I could have done this. Right? That would still be identified. Now I'd be estimating one extra error variance compared to what I'm going to go back and do it the way that's on your output, but this would be legit, but I have to have the first and second be constrained to be last and next to last to get this to work. Okay. Well, it's always going to be the first and second, and it's always going to be the last and next to last. So yeah, so I mean, again, I think this is the kind of thing that you sort of figure out as you're getting to know your data. So I saw that the residual variance for read 11, the disturbance variance for read 11, was different than the disturbance variance for the other ones, which led me to think, well, maybe then the measurement error variance might be different, like that, because again, the disturbance variance in that case is a combination of the error and the unexplained. So it's like, well, I definitely don't want to. So I was thinking, I don't want to constrain all of them to be equal to each other, but it sure looked like maybe it was reasonable to constrain a bunch of them to be equal. Like maybe I could even constrain all but 11. So, I think it's a combination of obviously theory and also just sort of knowing your data. So in this case, this is more like sort of looking at your data. And these kinds of decisions, I mean, you need to make and you need to explain. But generally speaking, like, whether you, estimate 2 or 3 error variances is usually not going to that's not really going to change like your parameter estimates very much. But, but again, you want to think that through and you want to be like thoughtful about it. Yeah. Oh, I wish they would give it different names. So let's see. Tech 1 gives your Tech 1 actually it shows what parameters you're estimating and it numbers them, which might sound really stupid and is usually not that useful, but sometimes it is. Because how sometimes like if you get a warning message from M+, it might say like, oh, whatever, get some warning and it says problem with parameter number 23. Okay, well, if you want to know what parameter number 23 is, put in Tech 1, and Tech 1 will actually spit out all of the parameters. We can look at it in a minute. All the parameters that are being estimated, and then it'll give them numbers. So it can actually be useful to have. Now, Tech 3 and Tech 4 are the two that I always. Tech 4, I think, gives you your correlations among your latent variables. So it's the latent variable correlations. Tech 3, I think, is the correlations among the parameter estimates. Tech 9 gives you your error messages. A bunch of the techs that are in the teens are all sort of related to mixture modeling. I can't honestly remember what 5, 6, 7, and 8 are. I feel like I never use those. I don't even know if there are Tech 5, 6, 7, and 8. But I will say that, like, if you go to the M+ manual, it will tell you exactly what each of the techs are. It is not intuitive. They are just numbered in the order in which they built them into the program. So like, I truly sometimes will be like, oh, I want this. What's the tech again? Especially with some of the mixture modeling stuff. Like, it's like, oh, is that Tech 14 or is it Tech 15? But you can always go to the manual to find out. Okay, so let's go ahead and run this. Okay, that didn't take long. So let's actually, I'll scroll down to Tech 1 here, right? So it's really ugly looking, but here you go, the Tech 1 output. So you can see that, like, here it is. So like this is parameter 1, this is parameter 2. Here are the, so it's numbering the parameters, and the thetas here, these are, oops, the thetas here. Okay, actually, look at this. You should be able to tell me. You see how there we've got a 1, 1, 1, 2, 3. So what parameters are the thetas for, what are these? Variances, and you can see that they've been, that's why they all have the number 1, right? And then error variance for school read 11, it's got the number 2. C 12 and 13, because they both have parameter 3. No, this is Tech 1. Yeah, this is Tech 1. Tech 4, let's check my memory and see if I was right about Tech 4. Should be the, yeah, so it's giving you, here you go. So this is giving you, right, the estimated means for the latent variables and their standard errors, and then the estimated covariance matrix for the latent variables, their standard errors. So basically it's giving you the latent variable variance covariance matrix, which isn't the same thing as the model implied variance covariance matrix, right? The model implied variance covariance matrix is like the model implied variance covariance matrix for our observed variables based on our model, our latent variable model. But this is like, hey, there are some I've run a latent variable model. What are the model implied correlations among my latent variables? Like read 8 and read 9 are latent variables. What's the model implied covariance for those? So, all right. Back up here to our model results. So let's take a look at our chi-square. Okay, so in this model, again, because we have more time points, right? We've got a higher degrees of freedom than when we were counting earlier with like a 3 or 4 time points, but still pretty low DF model. We have 7 degrees of freedom, and our chi-square is 6.762. So what would you say about the fit of this model? Good, right? Much better fitting model than our other model was. The RMSEA, again, was like 0.1 something before, remember that? Now it is 0. So, you know, with the 90% confidence interval goes from 0 to 0.4048. And the CFI and TLI, which looked okay before, they didn't look horrible, but they certainly didn't look as good as they do now, right? They're now 1. So like clearly we're getting a much better fitting latent variable model when we use the latent variable model. And my experience has been when I have with different data sets fit, you know, the single indicator latent variable autoregressive models versus like the observed variable models, this is a very common finding. Often the observed variable models, not only are you not dealing with measurement error, they just don't fit well. They just don't fit nearly as well. And the latent variable models fit a lot better. Okay, so now let's go to our standardized results here. Oh, by the way, here are our residual variances. Before we get to the standardized results, let's just look at our unstandardized residuals. Because remember, so the school reading 8 through school reading 13, those are our indicators. And remember that I constrained the variances for 8 through 10 to be equal. And you can see that here, right? 12.25. They're all constrained to be equal. Look at the residual variance for school reading 11. It is actually substantially bigger than that, right? It's 21.83. And then look at 12 and 13. Like the residual variance for those two is actually worryingly low, isn't it? Right? Those residuals are really low, and they're not significantly different from, right? Look at the p-values, 0.959. So like basically the error variance, there's almost no error variance at in 2012 and 2013. So now that you look at this, you can see why I went with 3 different error variances. Like it's pretty clear when you look at this that if I constrain them all to be equal, that's not going to work so well, right? All right. Again, these are the measurement errors up here. The school reading. These are the disturbance variances. Now we have that nice partitioning of the measurement errors and the disturbance variances. Okay. So let's take a look at our standardized results. And remember, we had like what, 0.95s before in terms of those autoregressive paths. We're not constraining these autoregressive paths to be equal here. Although, you know, it looks like maybe we could mess around with that, but holy crow, 0.99. So those stability coefficients are, you know, very near 1, right? Now, this is a place where it would be interesting to ask if they're statistically significantly different from 1. We don't know that. But they're super, oh, I'm sorry, hold on, those are my by statements. Well, I got confused because I know my on statements are almost as high. Sorry. Okay, here we go. Here are my autoregressive paths. Bad me. 0.98, not 0.99. My bad. Still, super. This is a crazy example, actually. Super high. My stability coefficients are super high. So just to remind ourselves then, though, these, if I square this, that's going to give me my reliability. So 0.99 squared is going to be, I don't know, 0.98 or something. I don't know, 0.97. I don't know, it's going to be really high. We'll see in a minute. Okay, so unbelievably high reliability. Oh my gosh, look at this. Look at the reliability here. Why does this make sense, by the way? I mean, I'm like, given what we just saw about those error variances before. Remember I said those error variances for 12 and 13, they weren't statistically significantly different from 0? Well, look, like this is 1. So basically, this is saying like, I'm basically explaining all of the variance in school reading 12 with my latent variable for school reading. My latent variable is explaining all of the variance. I mean, and again, technically not all, there was that 0.95 left over, but basically essentially all, right? And what was left was not statistically significantly different from 0, which is weird, but okay. So not such a problem with reliability here, right? But yeah, because the by is always factored, right? It's always something by something is this is measured by this. So it's always, you got to remember your syntax. This I should have made. I kicked myself. I should have made these names. I should have named the reading factor ones factor something, because the names are too similar, right? You have to remember that reading 8 is the factor and school reading 8 is the indicator. So maybe I'll change that for next time I do this example, because I found they're just too similar. But yeah, so these by statements are actually about measurement, and the on statements are always my autoregressive. And you can name things anything you want. So maybe give yourself names that make it really obvious. Yeah. That's exactly right. That basically that the observed score, all the variance in the observed score is being, or virtually all the variance in the observed score is being explained by the latent score, and there isn't statistically significant error variance. So they are basically redundant, right? They are basically one and the same, which, okay, that's not going to happen that often, but all right. So here are my on statements. But again, really, you can see these are higher than they were when in the observed variable framework. That much higher, because again, I don't really have a major unreliability problem, do I? I mean, my reliabilities are very high, so I wouldn't necessarily expect there to be a huge difference, but they were already high and now they're higher still. So, all right, so that's that. And then, okay, here we go. Here are my, again, my residual, you can see here my residual variances for 12 and 13, which are my measurement errors. There's just nothing, right? So let's look at these R squares. These are my reliabilities. This is the square of those coefficients. So 0.99 whatever squared is 0.981. And the other 0.99 squared is, again, 0.979. And so you can see that the R squareds here are really, really high. So I have incredibly high reliabilities. I have incredibly high stability coefficients. Not always going to find things that are that high. Okay, questions? Does that make sense? Yeah. Generally speaking, yeah, you're going to want to look at the standardized results. Like I sometimes look at the unstandardized disturbance and error variances, right? Like, but yeah, in terms of the paths and the reliabilities, to get the stability coefficients and to get the reliabilities, you're always going to look at the standardized. And it's the standardized paths that give you the stability coefficients, and it's the R squareds that give you the reliability coefficients for the effect of the latent variable on, or for the, reliability of the latent variable. Okay. Reliability of the observed variable. Yeah, I mean, like, if you look at the standardized error variance, then what you're getting is if you look at the standardized error variance, you're getting a proportion that's explained and unexplained. So that's useful, but I might also want to see, like, in raw metric, how much is that error variance, not just what the proportion is. So, okay. So that is this model. So fits really well. That's great. Let's see. Oh, yeah. So the next thing we want to talk about is, oops, I just closed that. Hold on. Wait, say that again. So if you go by hand from, what is it? Read.
Like I would square.
Uh-huh. Yeah, but that's because because this is just getting rounded to 3 decimal places. Yeah. I mean, again, yes, because you're getting things rounded at 3 decimal places. So if you could see to more decimal places, you would see that the one is actually, that 1.99 is actually a little bit lower than the other 0.99. That's why you're seeing that slight difference. I mean, for all intents and purposes, it's probably not going to matter that much, like 0.981 and 0.979, like you would both round both to 2 decimal places, they're both 0.98, but yes, but that, if you want to get the right thing to 3 decimal places, you should use the R squared. All right, so let's go back, hold on, and let's talk about this for a second. Notice that the variances, let's see here, the residual variances for, here's read 8. The variance for read 8 is like 619.381. So that's the variance of the latent variable for reading 8, okay? And remember, read 8 is, if you think about the model, it's an exogenous variable. So this is the total variance for read 8. And if you look at the variances for read 9 through read 13, these are actually disturbance variances. So they're the proportionate variance in read 9, 10, 11, 12 that is not explained by the prior variable, right? So this is a place where it's really obvious that these are sort of, that the exogenous variance is sort of telling, I mean, it's something very different. It's the total variance in the variable. It's the total variance in the latent variable versus these are the unexplained variances, right? That makes sense? So now let's go back here for a second. I want to talk a minute about stationarity. Current slide. Okay, Couple of these slides. Okay. So when we're thinking about stationarity, this idea of well, maybe we'll go back. So stationarity is this idea that comes up a lot in time series analysis, okay? So a stationary time series is a series whose properties don't depend on the time at which the series is observed. So like, if you think about it, I'm trying to estimate this model, this process, but I don't want my results to depend on the exact timing of when I'm like measuring this stuff, right? Like it would be kind of problematic if like, oh, I measure these things now and I get this answer, but if I measured like a couple months later, I'm going to get a different answer, right? So this idea of stationarity is like, okay, I've got stationarity in the sense that it doesn't really matter when I measure these things. I mean, I need to have the same distance lag. I'm not talking about that, but like that I'm going to get the same answer whether I measure this stuff sort of the way I measured it or whether I measure it in another, if I measured it a month later. I mean, I'm saying a month, it doesn't have to be a month necessarily. So the idea there is that this statistical process that's generating this time series that it's not changing across time, okay? And stationarity is kind of there's a lot to know about stationarity, and we're just going to scratch the surface here. But like, here are some basic pictures of some processes, and you can see that like, if you look at the green picture in the first picture, image A, you can see that this is actually like a stationary series. There's some sort of thing going on, but like, whatever's happening seems to sort of be happening across time. If you look at the second figure, actually you have a mean. The mean is time dependent, right? So actually somebody asked a couple weeks ago, like, what about stationarity? And I was like, yeah, with growth models, like we're not making the assumption of stationarity actually. But like, so when we think we've got growth across time, we're not actually making these, like stationarity is not necessarily where, that's not what we're thinking about. But we could also have like time-dependent variance. So the variance of the variable is changing across time. That's also a kind of non-stationarity. Another kind of non-stationarity would be like, the covariance between variables varies as a function of time. And now, for the models that we've been talking about, actually, I've been allowing those autoregressive paths, those stability coefficients, to vary across time. And I said we don't have to make those stabilities the same across time. But if I wanted to impose stationarity to my process, what I would want to do is say, like in a stationary process, it should be that the variances are the same across time and the covariances are going to be the same across time. And so I would want to actually impose a restriction that all of my stability coefficients would be the same across time. And I would also want to fit the model with some constraints such that the total variance of the variable is the same across time. And this is kind of a tricky thing because remember, I just was showing you like at time, or even that we could say that the residual variance across time, actually. You could do it that way too. But like, remember I showed you that in my output before, I had a huge variance for time 1 because it was an exogenous variance. And then I had these disturbance variances at like times 2, 3, 4, 5, and 6 that really were the unexplained variance. So if I wanted to sort of test the assumption of stationarity, what I would want to do is constrain my stabilities to be equal across time, and I would want to constrain my disturbance variances to be equal across time. But really, I want all of my variances to be equal across time. But you see, if I can forget about the first time point for a second. You think about time points 2 through whatever. If I constrain the stabilities to be equal across time, right? And I constrain the residuals to be equal across time, the disturbances, then I'm actually going to get the same total variance, right? Because like the stabilities are the same and the disturbances are the same. So if you think about it, you're going to add those together, right? You can get to the, but here's the problem. The first time point is exogenous. And so that variance is going to look really different. And so I could kind of look at this, it would be really easy to look at the stationarity of the process by just constraining all of the disturbances and all of the paths to be equal. And that would really be giving me an idea about stationarity from times 2 on. But it doesn't tell me anything about time 1. Like, how do I know that the variance of time, like that the variance of time 1 is equal to the variances of time 2, 3, 4, 5, 6, 7, 8? You see what I mean? Does that make sense? And you might be thinking like, why do I care? And maybe you don't. Often you might not. But like, if you care about stationarity, then you would care. So here's the thing. I've got to find a way to be able to constrain to what I'm going to do is I'm going to trick M plus into estimating a disturbance variance at time 1. So I'm basically going to partition that total variance of 619 into 2 pieces. A disturbance piece, which and the other piece. And I'm going to have to do that. I mean, in some ways, I'm not really fully testing this, but I'm setting up something like a stationary series. I'm going to do that. I'm going to sort of trick M plus, and then I'm going to be able to, so I'm going to get a disturbance at time 1, and then I can constrain that disturbance at time 1 to be equal to the disturbances across times 2 through 8. Okay, now I know you're thinking to yourself, like, how on earth do I want to do this? And maybe you don't always have to do this, but let's say you do want to do this. I'm going to show you how you do it with a phantom variable. And a phantom variable is actually a really kind of a useful idea that will come in handy in other places in SEM for us. So it's like a good thing to talk about now anyway. All right, let's see. Was there anything else I wanted to say about stationarity before So again, so stationarity, we're really saying like the causal structure is not changing across time. And also, you know, it's not really the same thing as stability necessarily. It's really about sort of the stability of the causal structure. And so when we have stationary models, and this is really important, what we're really saying is that the model implied variance covariance is independent of the exact timing of the assessments. So, but again, if I really want to look at that, I'm going to have to impose constraints on the model implied variance of variable 1 so that I can actually compare it to the model implied variances for the subsequent time points that are in there. Okay, so how am I going to do that? All right, I'm going to create this thing that's called a phantom variable. Yeah. Yeah, right. That's what we want. Yeah. And then this gets even more complicated when you get into, which we're not going to get into today, but like cross-lag models, right? Because then we really need those cross-lags to be equal across time as well. But really, so really what we want is, okay, anyway, I'll leave it there. Because we only have 12 minutes left. So phantom variable, so here we go. This is what I'm going to do. A phantom variable, by the way, is not the same thing as a latent variable. You might have thought like a latent variable, that's already kind of not a real variable. A phantom variable is like, again, it's sort of a trick that we're going to use. It's truly just like a specter that we use in order to sort of mathematically get what we want out of M plus. So here's what we're going to do. We're going to create a phantom variable. Okay, this is our phantom variable right here. Actually, we're gonna have a phantom variable going into, so predicting read 8. Now read 8 can have a disturbance. Couldn't have a disturbance before, right? And so we're gonna get a disturbance for read 8. And so now the variance of read 8, we're decomposing into two variances. The variance of the phantom variable and the disturbance. And the disturbance variance for read 8 and the disturbance variance for read 9 are going to be constrained and equal. And this is why I say, because we're going to constrain these two disturbances to be equal to each other. And we're going to have to do that, again, to identify the model for sort of similar to what we had to do with the measurement variance. So in some sense, like I have to make that constraint. So I make this constraint that those are going to be equal to each other. And then I'm going to estimate the variance of the phantom variable, but I'm going to constrain the path from the phantom variable to read 8 be equal to 1. So it's almost like a latent variable on your latent variable. Think about it, right? Like, look at this. It almost functions in exactly the same way that we were talking about, like analogously to the measurement error stuff. So here, this phantom variable is like it's a phantom. This path is 1 to read 8, which is our latent variable. Now I've got a disturbance for read 8, which again is kind of like analogous to the measurement error that we had over here. But to actually pull this off, I got to constrain this disturbance. I've got to yoke it to this disturbance. I'm going to constrain these two disturbances to be equal. And by doing that, I'm going to actually basically take the total variance in read 8 and break it into a piece that's like this sort of explained and unexplained piece. And now I've got this disturbance, and now I can actually constrain all of the disturbance variances across all of the latent variables to be equal across time. Exactly what it's doing. I'm forcing read 8 to be endogenous and exogenous so that I can get my variance to be in the same kind of metric that I had for all of my other variables. Because otherwise, it doesn't make any sense to constrain the exogenous variance for read 8 to be equal to all of these, because all of these are unexplained variance, and this is the total variance. So I'm basically using this trick to like kind of crack it into two pieces. But I'm constraining the disturbances for 8 and 9 to be equal to each other. Yeah? That makes sense? Yeah? Okay, cool. All right. So, again, you can do this to achieve stationarity, but you have to be able to constrain all the endogenous paths to be equal. Because again, what we're really going for is the model implied covariance matrix should be independent of the timing of the assessments. And then I think, the latent variable is going to have a mean of 0 if we've got means in the model. If you don't have means in the model, you don't have to worry about it. And we do have to set the disturbance variance of the first variable equal to the disturbance variance of the second variable. So how am I going to do this? I'm going to say phantom. The phantom factor is measured by read 8. So now read 8 is an indicator, read 8, the latent variable looks like an indicator of the phantom latent variable. Again, you're not going to need this whole thing about phantom at 0 if you don't have any, you don't have any means. And then read 8 and read 9, I'm constraining those disturbance variances to be equal. So, and so I can then figure out, if you think about it, the variance of the phantom variable plus the disturbance variance at time 1 is going to be equal to the variance of the phantom variable plus the disturbance variance at time 2, right? Which is going to be equal to the total variance of the latent variable at time 1. So when we get the variance of the phantom variable, and this is an important distinction, it's the variance of the phantom variable is not going to be the total variance at time 1. So if you were to look at that, you would be like, hey, that's not the same as the 619 I saw. That's right, it's not the same. It's going to be the variance of the phantom variable plus the variance of the disturbance variable are going to equal that 619. So let's do this and see it. It's pretty cool. I don't know. Okay, so what? The total variance is going to be the variance of the phantom variable plus the disturbance variance. All right. So here we go. Here's our input file. So you can see this looks very similar to the input file we had before. Everything up here is the same. The only things that I've added are right here. So the first thing is I said phantom by read 8, right? That's that phantom latent variable. And again, I sort of said the phantom variable has a mean of 0. I have to say this because I have means in my model, but notice again, you don't need to say this if you are just using a variance covariance matrix without means. So, and then read 8 and read 9, we're constraining the disturbance variances to be equal. For read 8 and read 9, we run this model. And, okay, first thing you should notice is, how does the model fit? Oh, where did my model fit go? What do you notice about the model fit? It is identical to our last model. So this is just a nifty trick, right? This isn't a different model. This isn't a nested model. This is an equivalent model. This is just a way of partitioning the variance so that I can constrain all of my disturbance variances to be equal. That's really what this is about. So, which I haven't done here, by the way. I've only constrained the two disturbance variances I needed to constrain. Okay, so go to our variances. Here we go. So see this? The variance for the phantom variable is 596.081, right? And the variance for read 08, which is now the disturbance variance for read 08, is 23.297. And notice that's yoked to the residual variance or the disturbance variance for read 9. And if you take that 23.297 now, I mean, within rounding error, right? Like it may not be exactly identical, but it's going to be darn close. If you take that 23.297, which is the disturbance variance for read 8, plus the phantom variance for read 8, was that 596.081, those two things together are going to equal the total variance for read 8. Yeah? Okay, so again, this model is an identical model. The fit is the same. The reason that we would do this, though, is if we really wanted to really test the assumption of stationarity, then we need this phantom variable approach. And then the next thing we would do, actually, to test the assumption of, we could do, not a lot of time, but the next thing we would do to test the assumption of stationarity would be to constrain all of our causal paths to be equal, or I shouldn't call them, all of our stabilities to be equal, and also constrain all of our disturbances to be equal. So it's those two pieces. So when I said it's not the same as stability, just constraining the stabilities to be equal is not enough to get you to stationarity. You have to constrain the paths to be equal, those autoregressive paths have to be constrained to be equal, and the disturbances also have to be constrained to be equal. All right, yes. Yeah, but see, if you look at it, because we haven't actually added any freely estimated parameters. It's a good question, but notice, you're right, I did do that. But I'm estimating the phantom variance instead of the exogenous variance. And I've got a disturbance variance in there, but it's yoked, it is constrained to be equal to the disturbance variance of read 9. So that's not an extra parameter. So all I've done is, instead of estimating the total variance for read 8, I'm estimating the phantom variance for read 8, right? And then I'm constraining the disturbance variance for read 8 to be the same as the disturbance variance for read 9. And of course, the path is 1 and the mean is constrained to be 0. So I actually haven't added any parameters. That's why I say it's kind of like a trick, right? It isn't like, this is a nifty trick that we use to be able to kind of partition things the way we want them. But the model is statistically equivalent to the last model. And again, why I would do this is because I want to be able to, because I want to be able to constrain all the disturbance variances to be equal to each other. And so I'm finding a jiffy way to get a disturbance variance at the first time point so that I can constrain it to be equal, so that I can, make this assumption of stationarity. If you don't care about stationarity, you can just disregard everything I just said, except for you can't totally, because I think I make you do this in the homework. So, but you wouldn't go through all this trouble unless you were kind of caring about that, right? Like, you can run these autoregressive models without phantom variables and without all of this rigmarole. But if you care about stationarity, and often we do, then this is kind of the route to get there. Questions? Yeah. Because it's because it's not an observed variable. Not an observed variable. So we never define our latent variables either, right? So this is like a latent variable, but it's a special type of latent variable. It's like a mathematical trick latent variable. And I'll just say one more thing and I'll let you go, because I know it's like 1 minute late already. I mentioned that, like, another use for phantom variables is, like, imagine if I had an autoregressive model and I had like measurements that are always a year apart, but like suddenly I have, for one, like, data collection, there's a skip. So it's like a year apart, and then then it's 2 years apart. You can actually use the same kind of strategy. You can create a phantom variable in that spot where, like, that year would be. So let's say, like, if I didn't have 11, right? I could create a phantom variable for 2011, and I use the kind of the same strategies here. It's not a real variable. I'm going to make some constraints, but I can do that so that basically what I do is I take the autoregressive path that would have been between, say, 10 and 12, and I'm going to have, like, I'm basically going to split it into 2. I'm going to constrain those 2 paths to be equal to each other. And that way I can actually get an estimate for autoregressive paths that have the same time length. So that's another use. That's probably an even more important use of the phantom variable sort of approach. So we can use these phantom variables. They're sort of like a way to trick the program to get parameters that look the way we want them to, but we're not actually adding any more parameters to our model. Yeah. Oh no, yeah, like you could have something like that. You could literally have 2 phantoms in a row. But again, it doesn't give you any more information than you really have. You'd be constraining that stability coefficient, that B parameter, to be equal between years 1 and, like, your X and Y, your Y and Z, your Z and Q, right? So then but the phantom will allow you then to basically take what would have been that stability coefficient and break it up into these different pieces, so that you can, again, sort of, test whether the stability is similar across time. But again, you don't have any more information there. So you're going to have to assume that those stabilities are equivalent for the place where you don't actually have any more information. There are lots of other places where we use phantom variables too. I don't know. I think phantoms are really cool. It's like as if latent variables weren't, like, latent enough. Now we have, like, imagine, like, latent variables are already like not there. Right now we've got like totally imaginary latent variables. So like you kind of feel cool and you're like, yeah, my mom's got a phantom, not a latent variable, phantom variable. Anyway, all right, I'll stop there and I'll see you all next week.
Thank you, Betsy.
Hold on one sec. Let me just turn this off. I'm sharing my screen. Stop sharing. Stop recording. Stop.